A 32-inch pump is to pump 24,000 gallons per minute of water at 1170 RPM from a reservoir that is open to atmosphere. If the head loss from the reservoir to the inlet is 6 feet, where should the pump be placed to avoid cavitation? So as we look at this, we're going to apply our energy equation to things. I don't have a picture, but they've kind of described in the problem what's going on. And so we can just sketch out a picture here. I have a reservoir. I have some pump. It's drawing water from the reservoir. And I know that my total head loss is 6 feet. I have the vapor pressure of the water at that point also. And so what I'm trying to figure out is, what is that distance? So we'll call this Z1. That'll be Z to the suction side of the pump. And so we need to avoid cavitation. So as I take a look at it, I have my charts here. This bottom one is for 710 RPM. So that's not what we want. We need 1170 RPM, which is this upper graph up here. And I want to calculate out what the net positive suction head available is. So I'm running at 24,000 gallons a minute. So if I follow that line up and then follow this over, our net positive suction head required from the graph is, let's say, 37 feet. And so now we go and we'll use our energy equation and solve for that. Now, of course, energy equation, we've got to make a couple assumptions. And as I look at that, we'll put them here. My assumptions, steady flow. Nothing in the problem says that it's unsteady. Second, we need a constant density, incompressible flow. Water's generally incompressible, we're good there. Last thing we need is a constant temperature flow. There's nothing in the problem that says anything about temperature changing. So as I look at my energy equation, pressure over gamma plus V squared over 2G plus Z at 0.1 has to equal all of this stuff at the suction side of our pump plus the head of the turbine minus the head of the pump plus total head loss. Taking a look at things, no pump and no turbine in that control volume that we're dealing with. We're going to say that Z1 is 0, because remember, we're actually going to try to find Z2. Surface of the large tank, that's going to be 0. So we're left with our atmospheric pressure vapor head, our atmospheric pressure head, everything coming into the pump, and H total. Now I'm going to want to add and subtract my vapor pressure head, because once I do that, I will be able to take these three terms here and say that I have my net positive suction head. Net positive suction head available from those three terms, plus my height, plus my total head loss, plus my vapor pressure head. So now if I rearrange all of this, basically bring everything over to the other side, the available head that we have, actually, let's not write it that way because we're actually trying to find Z height. So let's move the other stuff over. So the height of my pump is going to be equal pressure over gamma minus net positive suction head available minus H total minus the vapor pressure head. So we have atmospheric pressure, and so we know that's 14.7 psi, so pounds per inch squared. Subtract from that the vapor pressure head, which is given to us in the problem, is 0.26 pounds per inch squared. We're going to divide that by water. Specific weight of water is 62.4 pounds per cubic foot. This obviously does not work out because that's going to give us pounds per square inch on the top. So what we're going to do is we're going to multiply by 12 inches over 1 foot. And then we will square that to get square inches and square feet. So we'll continue here on the next line. NPSH available. We look that up in our chart, and that's 37 feet. And then the problem told us we have 6 feet of head loss total. So if I go and I calculate this out and plug all the numbers in, I'm going to get told that I have negative 9.7 feet. So that tells me to have this operate under these conditions that my pump has to be almost 10 feet below the surface of the water. Otherwise, we're in danger of cavitation.